She's visiting us for today, unfortunately, only for today. So please take it away.
Yeah. Okay. Thank you very much for the invitation. So today I want to talk about the cosmological perturbations of axion dark matter at large scales. So first I want to start with a brief overview of axion dark matter cosmology, and then I'll focus on recent work presenting you a general analytical treatment to axion perturbations at large scales. If time allows, I will show you some preliminary results from an ongoing project about CMB constraints on axion isocurvature and conclude. Okay. So let me start with a review of axion dark matter. So axion is one of the two classic benchmark dark matter models. The other one is thermal dark matter. So the minimum mechanism for axion to be dark matter is a misalignment one mechanism. So initially the axion is frozen in the field space. When the Hubble drops around the axion mass, the axion start to oscillate, and the oscillations redshift as cold matter with equational state being 0. So roughly speaking, there are two types of axion cosmologies. So here actually, for most of the talks, I focus on QCD axion, but a lot of the discussions actually could be generalized to axion-like particles, ALPS. So the first type of axion cosmology is the so-called pre-inflationary axion, QC axion. So in this case, PQ symmetry is broken during inflation. In addition, PQ symmetry is not restored during pre-reheating or reheating after inflation. So the key defining feature for this scenario is that the massless axion is already present during inflation. So that's I will actually call this I'll call this axion field theta. So this theta is angular mode in the of the PQ scalar after PQ symmetry is broken. Okay, so in the pre-inflationary scenario, so the axion takes a single uniform central value of initial misalignment angle. Since axion, the massless axion is already present during inflation, it will fluctuates. And its fluctuations are independent of the inflaton fluctuations. So we say the axion actually has a primordial isocurvature perturbation. And this fluctuation, delta theta here, this amplitude is, the delta theta is set by the ratio of the inflation Hubble and then the axion decay constant, okay, during inflation. So after inflation, the axion will become dark matter through the misalignment mechanism. And this primordial axion perturbation will, like isocurvature perturbation, will lead to the cold dark matter isocurvature. So here I just want to show you a cartoon picture of these two different perturbations in cosmology, curvature, or also known as adiabatic, versus isocurvature. Again, this is a very rough cartoon pictures. So we have different cosmic fluids, dark matter, photon, neutrino baryons. For the curvature adiabatic perturbations, that these perturbations of these different fluids are proportional to each other. And for the isocurvature ones, they're different from each other. Okay. Again, I'll make this definitions of curvature, isocurvature more precise later on. But here, just give you a rough picture.
Turn off the light because your slides are pretty.
Oh, sorry for that.
No, I like them, but I may not be able to turn off the light correctly. It's always the last one.
Okay. Okay. So there are both pros and cons for the for this pre-inflation for the different types of axion cosmologies. For pre-inflation case, the main disadvantage is that the isocurvature perturbations. So actually, current CMB hasn't observed data from data. We haven't observed isocurvature perturbations. Instead, from the Planck data, actually the Planck data actually sets a pretty strong constraint on isocurvature. So assuming this, the primordial isocurvature has a flat spectrum, okay. So then the Planck bound actually bounds on this ratio of the amplitude of the primordial isocurvature spectrum and divided by the normalized by the amplitude of the curvature spectrum has to be below like 0.04, okay, roughly 0.04. So when we apply this constraint to the QCD axion dark matter, and assuming QCD axion is 100% dark matter, this could be actually translated to an upper bound on the inflation Hubble scale. So for axion decay constant about 10 to 11 GeV, that's actually for the QCD axion could be the entire dark matter with like order 1 misalignment angle. Then the inflation Hubble is bounded to be below 10 to the 7 GeV. So another way to say this bound is that this shows that the QCD, the minimal version of the QCD axion dark matter, like through the misalignment mechanism, that we, as the dominant component of dark matter is incompatible with high-scale inflation, the leading like inflationary scenario. Another way to think about it is that if for the next like generation CMB experiments, they observed the primordial B mode and mirror tensors to scalar non-zero tensor to scalar ratio, then the QCD axion, the minimum version of the QCD axion dark matter as the dominant component dark matter will be severely colored. Okay, that's actually also like one early a while back when Bicep reported they had observed the B mode.
Sorry, I don't understand this thing. So you are assuming that axion is the dark matter, correct?
So yeah. So here
if it is dark matter, then the perturbations should be curvature perturbations, because we know that dark matter has curvature perturbations, not isocurvature perturbations.
Oh well, see in this case, for the pre-inflation case, the QCD axion dark matter will have both curvature and isocurvature perturbations. I always plan that, actually. I always plan that.
Oh, so you are saying there will be some admixture of isocurvature,
yeah,
but
yes.
there will also be curvature.
Yes,
okay.
yes.
Okay.
That's my the main focus on my first topic. This is still review. Okay.
Okay.
So what's the advantage of like the pre-inflation case? So for QC axion, like one serious theoretical challenge is for QC axion to be the solution to strong CP problem is the QCD axion problem, quality problem. It just says it was tiny explicit breaking of like PQ breaking encoded in high dimensional operators suppressed by the Planck scale could spoil QCD axion as a solution to the strong CP problem. So one leading solution, okay, so it's not just one solution, but one leading solution is the extra dimensional axion, where in this case the axion is actually realized as a zero mode of a high dimensional gauge field. So in this, in the scenario, extra dimensional axions, actually the PQ symmetry is always broken. Okay, so then by default, the extra dimensional axion is the cosmology of extra dimensional axion is always pre-inflationary. The axion is always there, so it's present during inflation. So, so this is a quick review of pre-inflationary. So now also review very briefly the other type of axion cosmology, the so-called post-inflationary QCD axion. So in this case, the PQ symmetry is not broken during inflation. All PQ symmetry restored during reheating or preheating, and then broken after like inflation. So, so the initial misalignment angle could take any random value from a uniform distribution between 0 and pi, and with a calculable variance. So, since PQ symmetry is broken after inflation in this case, there will be a lot of topology defects from the PQ symmetry breaking. There's axion strings and domain walls. So in order to have a viable cosmology, these topology defects could not be stable, they have to decay. And that decays will actually contribute to the abundance of axion dark matter on top of the contribution from misalignment mechanism. So this, kind of was pointed out a long time ago, but to find out the precise value of this contribution actually requires very challenging and sophisticated numerical simulations. This was implemented by several different groups over the past few years. And there's still ongoing work. So, to some extent, the disadvantage and advantages of the post-inflation case is the opposite, of that for the pre-inflation case. So again, start with the disadvantage. So this actually work by Chen-Shu here. So that's it's challenging, so not impossible, in the post-inflation case to have a high-quality QCD axion without cosmic domain wall problem. So basically, in this case, you have like different axion, it's in the different minimum and PQ field. You could easily have all these cosmic domain walls, and to solve the cosmic domain walls, you you could introduce some PQ breaking that was again spoil the quality of the QCD axiom.
Sorry, remind me, you said, but I can't remember what quality refers to?
So just say like even you have like some tiny explicit breaking of PQ symmetry by high dimensional operators, very high dimensional operators suppressed by Planck scales that will screw up the QCD as a solution to strong CP problem. Yeah. So also the advantage of this post-inflation is also pretty clear that there's no axiom present during inflation, so you don't have like this isocurvature problem, okay, at least at large scale. On the other hand, on the small scales, there could be very rich small scale phenomenon, axion stars and mini clusters, and many people study, including you, okay. So that's actually all I want to say about this two general axion cosmologies. Okay. So now I want to move on to discuss actually my recent work. So analytical treatment to axion perturbations at large scale. So this is work done with Itama, a lady who used to be a postdoc at Brown, but now moved to Notre Dame. And pre-Chakra body is a PhD student at Harvard, and the supervision of Cora DeWalking and Maris, and he's currently a postdoc of Daniel Baumann at International Max Planck Center in Taipei, and also University of Amsterdam, and also Maris back in Harvard. So let me talk a little bit about motivation for this work. So I think this is a this is a very well-known fact for for axion perturbations. Actually, at super horizon scale, QCD axion dark matter perturbation is adiabatic perturbation plus isocurvature perturbation, which is isocurvature perturbation. Dark matter isocurvature is from the primordial one in the pre-inflation case. So this is so well known, and also this behavior at super horizon scale actually sets as the initial condition for like subsequent evolutions once the modes enter the horizon. So and it's basically the initial condition for all the numerical studies of the axion perturbations with all these different cosmological codes. But at least I was even though this kind of already textbook level fact, it was I feel confused for a while that how is this adiabatic part generated for long thermal dark matter for other axion. In the post-inflation case, I actually could come up with a hand-waving argument. So because PQ symmetry is broken after inflation, PQ scalar is initially in thermal equilibrium with the standard model, and they share the same perturbations. Then after PQ symmetry breaking, axion actually gets perturbation from the PQ scalar. So the origin of the adiabatic fluctuation is less mysterious. But in the pre-inflation case, it seems a bit more mysterious. It's the axion is very feebly interacting. It's never in equilibrium with the standard model. So how does the axion acquire the perturbations proportional to those of photons? And also, like we say, in the pre-inflation case, the axion field is already present during inflation, has its own isocurvature. So how does this primordial isocurvature convert into dark matter isocurvature later on? What makes me further confused is that in the case for QCD axion dark matter, actually the story story could be pretty complicated. Like the QCD potential, at least during the QCD phase transition, is pretty complicated. It could be temperature dependent. It's not necessarily quadratic. It could be high order terms. So and also there are a lot of axion models to explain the radical abundance. In addition to like the minimal model, you have a misalignment in the like radiation domination. There are other variants of misalignment models, like you could have early matter domination. You have like second phase of like matter domination after inflation with a second reheating that will actually be able to dilute the axion radical abundance and make the actually change the parameter space that could lead to the right radical abundance. So and also recently the kinetic misalignment and all of these different like axion models. So like it could happen like with different cosmic background evolution. You could have like in the minimal scenario, the oscillation happens in radiation domination, and then in the other scenarios could happen in matter domination and so on. So does this cosmic background evolution have any impact? So of course we look into literature since it's such a well-known fact. Maybe there should already be some explanations in literature. But as far as we could tell, there's a lot, whether it's like initial studies to like and to the more recent studies, a lot of these perturbation studies for QC axion and axion-like particle ALP just take a temperature-independent quadratic potential or assume like specific cosmic background evolution. Some of the studies, these studies are like just like do everything numerically. So so doesn't seem there's a clear explanation, even though everyone knows that's a fact, but no explanation for that. And also what makes me further confused is thinking about the background evolution. So here the theta, again, the theta is a dimensionless axion field. It's an axion field divided by the decay constant. So theta bar is the background. So this is the background equation of motion. You can see this equation, the V bar again is the axion potential evaluated with the background values. So you can see this equation clearly depends on the Hubble, okay, depends on the background. And so the evolution of the background and the resulting radical abundance clearly depend on the details of the axion potential as well as the background evolution. So indeed, like it's again has been studied by many papers in the literature that the temperature dependence, the harmonic effects due to the high order terms in the axion potential, and the background evolution could all be important for like the background evolution and the radical abundance. So it seems a bit mysterious. At least there's no obvious immediate answer to me when I first thought about it. Why does a large-scale perturbation like exhibit this universal behavior? Like it's just the adiabatic perturbation, like same as photons, plus isocurvature, if there's a primordial isocurvature. So that actually motivates us to take a closer look at this, trying to explain this well-known fact. Okay. So again, it's just what we look at as the axion perturbations as super horizon scales. So this is just for any perturbation with a wavelength k, like this will exit the horizon during inflation, and then stay outside the horizon for a while before it re-enters the horizon in radiation domination or matter domination, depending on the wavelength k. So the understanding of the super horizon mode could help us collect the relative recent past to the far past, okay, and also sets the initial condition for the modes once it crosses the horizon. So there is a very powerful theorem for this for super horizon perturbations in general. So this is a Weinberg theorem. So okay, so so the theorem states that whatever the contents of the universe, there's always a solution, the adiabatic solution, with a conserved quantity, scalar curvature on super horizon scales. It's easy to it is to prove it in the the conformal Newtonian gauge where you write the metric as this. Okay, here's the R. Since I already use A for the axion, the scale factor I'll call it R here, and the metric perturbations are encoded in both the time component and spatial component per psi and phi. Okay, so the scalar curvature is defined as this minus this metric perturbation minus the Hubble times the energy density perturbation for species I divided by the time derivative of the average energy density. Okay. So it could define the scalar curvature for all these different species, or it could define overall scalar curvature. So the adiabatic solution is that the scalar curvature for different species are all equal to each other. Okay. So then in other words, for the energy density, it just means the energy density perturbation, the ratio of the energy density perturbation, and the time derivative of the average background is the same for different species. Okay. So of course, if you look at the literature of cosmological perturbations, you'll see some that's actually a more popular way to write, maybe not necessarily more popular, but a more pretty popular way to write the adiabatic solution is actually write the energy density perturbation, ratio of the energy density perturbation and the background. Says for different fluids, this ratio of the energy density perturbation and the average background is proportional to each other. This actually is just a cool thing about the special case of this general adiabatic solution. So it happens when each component has a separately conserved energy momentum tensor with a definite equation state, Wi, and then you could relate the time derivative of the background energy density to the background energy density, as like 1 plus the equation of state times the background. Okay, so then this adiabatic solution just translated to that this energy density perturbation divided by the background and divided by 1 plus the equation of state is the same for different species. Or in other words, the ratio of the background, the energy density perturbation and the background is proportional to each other for different species, and the proportionality constant depends on the equation of state. Okay. So this theorem was proved by Weinberg in actually not in in the past, but not like 20 years ago, in 2003 and 2004. I should say that actually the existence of adiabatic perturbation and the solution actually is well known even before Weinberg's theorem Weinberg's papers. But as far as I understand, it was really Weinberg that levitated the existence of adiabatic solution to the theorem level. So actually, in proving the Weinberg theorem, Weinberg showed in general, actually for any scalar quantity S, the S could be not necessarily limited to energy density. Could also be pressure, or could be any other scalars, which I will show. Actually, the ratio of the scalar perturbation and the time derivative of the background is the same, is equal to minus this scalar curvature, a constant in time, times this integration of the scale factor. Okay, and then once we define the curvature perturbation, what curvature perturbation is like, then we could define this relative isocurvature perturbation, which is a difference between different scale between the scalar curvatures between the scalar curvatures for different species. Okay. So of course this probably you may know it very well, the Weinberg theorem very well. Okay. So and I think a very nice analogy, okay, which I don't fully appreciate before, okay, is that Weinberg theorem to some extent is a cosmological Goldstone theorem. So for Goldstone theorem in quantum field theory, which we're familiar with, is that the vacuum state spontaneously breaks a continuous symmetry. So then you have a Goldstone boson, okay, and this long wavelength of the Goldstone boson, the locally just mimics the shifts of the vacuum state, labeled by a phase. So in Weinberg's proof, actually, what he did is first actually construct a spatially homogeneous background solutions to the equations of state, to the Einstein equations. And then the spatially homogeneous background solution, the zero modes, actually breaks the diffeomorphism invariance. So then he promotes a zero mode solution to a physical mode with a non-zero wave number, and that gives an adiabatic solution, which I showed before. Okay, again, this is just summarizing all these equations just in words. So in that sense, this adiabatic solution is like the Goldstone mode of the breaking diffeomorphism invariance. So so basically, this Weinberg theorem, just this general theorem, powerful general theorem, just says like for whatever like fluids, whatever like its cosmological history is, will always have some adiabatic solution. So what we want to do is just given this general theorem, we want to understand like this axion perturbations, see how the axion perturbations realize the Weinberg theorem. Okay, so let's first look at the field, like axion field. Okay, so let's just try to write down the perturbation equation of the axion field and then try to solve it. So this is the action for the axion field. So again, I use theta, this dimensionless axion field. And it has a kinetic term and also has an axion potential. And I won't specify what potential it is. I'm not going to assume it's necessarily quadratic it's temperature dependent or temperature independent. So then we could follow standard procedure, right? Decompose the axion field as a background plus a perturbation. And for the background, this is the background equation I already showed you. And the solution for the background is sensitive to details of the potential and also to the background, cosmic background evolution Hubble. So now let's look at the perturbation equation. Okay, let's look at the linearized perturbation equation in the K space. Okay, it could be derived through the standard procedure. Okay, so you could see it's a pretty complicated equation. Okay, let me just plan like group terms by their physical meanings. Okay, so the first three terms are just the homogeneous part of this equation, just the differential operator acting on the perturbation, the K mode of this perturbation. Delta theta K is just the perturbation with wave number K, okay, the mode with wave number K. So then the remaining three terms, okay, so are the source terms, okay. The first two terms actually are the sources from metric perturbations. This is just because axion field coupled to the metric, okay. So they depend on this psi and psi and phi. These are metric perturbations, in the conformal Newtonian gauge. Okay, and then there's an additional term. This additional term is proportional to the temperature perturbation, delta T, okay, again, the K mode of the temperature perturbation. So this is the source term from the temperature perturbation. It exists if like axion potential is temperature dependent, okay? So it also depends on derivative of the potential with respect to the temperature, okay? So this are actually at a microscopic level, it just comes from axion, the interaction between the axion and the radiation, in particular gluons. So this equation, so it looks pretty complicated, but there exists like an analytical solution, in the small k limit. So this is super horizon limit where we have the physical wave number below the Hubble. Okay. Actually, the most general solutions depend on actually contains three terms. Okay. So the AK, BK, zeta k are constant in time. So the theta initial, again, the initial axion value, and the theta bar is a background solution. Okay, I don't know whether you're familiar with it. Certainly, I don't see it anywhere. This solution showing up anywhere in the literature. Even though the physical interpretation of this these solutions are also well known, but I haven't never seen this solution before. So it looks complicated, but I just want to emphasize one key feature for a moment. You can see that all these three terms, they all depend on the first term depends on the derivative of background with respect to the initial axion value, and second depends on the derivative of the axion field with respect to the initial velocity, and third term depends on just the general velocity of the background. Okay. So in other words, what the general solution for the axion perturbation in the superhorizon limit is entirely determined by the family of the background solution. So you could have, as I said, there are many different axion models that could give rise to the same radical abundance. You could have you will have different potential, could have different cosmic background evolutions. So they would give rise to different background evolution. And so the perturbation, axion field perturbation, will also vary in different models. But this relation between the perturbation and the background, this solution holds in all in general for all these different models. So to understand this solution a bit better, and also understand how this leads to this well-known fact that axion perturbation is adiabatic plus isocurvature in the pre-inflation case, let's actually take a simplified look at the simplified version. So here I'm going to make a bunch of assumptions to simplify the general solution. Okay, just to make hopefully make it easier to understand. So let's assume a universe is dominated by a single fluid with a scale factor proportional to temperature to some power. And also assume that it's anisotropic, stress-free, okay? And also axion is frozen initially. Again, a lot of these assumptions are necessary, just it's really just for me to simplify the solution from the most general one to this to the simplified one with two terms. One is just depends on the derivative of the background with respect to the initial misalignment angle, and the second one is just proportional to the velocity. So now we could take a look at the physical meaning of each term individually. So the first term is really the solution to the homogeneous part of the axion field perturbation equation. Okay. This is actually the isocurvature axion field perturbation. And the second term, is actually the particular solution to the full inhomogeneous perturbation equation. So actually this term is the example of Weinberg's adiabatic solution. So just remind you that adiabatic solution is that for any scalar quantity, the perturbation of the scalar quantity divided by the time derivative of the background is the same for any is the same. And we could actually given all these assumptions, we could also calculate could find that the other factor should be the time times the metric perturbation. So in this case, the scalar quantity is really just the axion field. Okay. So and for this the adiabatic part of the solution of this general axion field perturbation, there's actually more intuitive understanding where it comes from. So say again, consider a case where axion is initially frozen, okay, with zero velocity. So that just the axion field is axion is in the dark energy phase. It doesn't move, so there's no perturbation at all. Okay. So when the axion starts to move, the axion field starts to see the metric and temperature perturbation, while the motion of the field. So why that's that's why this perturbation is proportional to the axion, the velocity of the axion field. So as I mentioned before, that depending on for different models, that you will have different background evolution. So then you will have different perturbations, the axion perturbation. So indeed, the perturbation will look different in different models, but this proportionality relation between the axion field perturbation and the background, actually the time derivative of the background, this relation is independent of the potential, and also is true for scenarios beyond the minimal scenario where we have the misalignment radiation domination. Okay. So this is about the axion field perturbation, but of course in cosmology, what we care about is the energy density perturbation. Okay, so it's not. It's pretty straightforward to convert from the field perturbation to the energy density perturbation. So let's first talk about the adiabatic energy density perturbation. So in this case, from the adiabatic component of the field perturbation, we could translate it into the energy density perturbation, and unsurprisingly, that gives us adiabatic energy density perturbation. So again, if we do the calculation, and in the end you'll find indeed the energy density for the axion, what I call rho theta here, its perturbation, the ratio of its perturbation and its time derivative background is the same as that for the photon, as that for the radiation. Okay, and we actually you will do just a numerical check, like for a specific axion model where we have a quadratic potential, but we take the mass to be temperature dependent, and then we solve the perturbation equation numerically. Then that's shown as a blue line. So here, this the vertical axis is actually this cyclically averaged delta rho over rho bar dot. Okay, the horizontal axis is the time. Okay, so and the blue curve, okay, which are it's just a numerical solution for this the particular potential, and the orange dashed line is actually what we'll get from the analytical solution, this adiabatic analytical solution. So indeed, you see initially like the axion field doesn't move. Okay, it's potential energy dominated. So it's so it's in the adiabatic mode. So then you could have a pretty complicated evolution in between, but it's always stays adiabatic. Eventually, it will lock into this after QCD phase transition, when the axion potential, when this time dependence all disappears, then the perturbation just locks into that of the thermal dark matter perturbation. Okay. So even though in between that this could be pretty complicated evolution, but it always stays adiabatic. Okay. So now look at the, as I said, showed you before, that for the field for the field perturbation, there's an adiabatic part, and now there's an additional part, that's the isocurvature part. So let's again convert the isocurvature part of the axion field to the isocurvature energy density perturbation. So again, that's just it's a not difficult calculation. After some calculation, what you'll find is that the isocurvature defined as a difference between in this case, the scalar curvature for the axion and also the photons. So it's looks like this. Okay. So indeed, it's proportional to the delta theta, which is generated during inflation. Okay. But with all these prefactors. Okay. So actually, what it turns out, a kind of interesting small fact, which doesn't really have observational consequences, is that this is the isocurvature perturbation is actually time dependent during the QCD phase transition. If you calculate all these prefactors, actually again, if you just as an example, if you assume again quadratic potential with a temperature dependent mass, which is this is the case for. This temperature dependent mass is for calculated by latest calculations for QCD axion. Then you'll find that the isocurvature part actually is time from the early stage when the when axion is frozen, to the later case when the axion just oscillates coherently around the quadratic part of its potential, is actually the value changes. Okay. So of course, that for QCD axion, this a time shift of the isocurvature perturbation actually happens too early, so it's irrelevant for observational scales like CMB and large scale structure. But you could think about maybe in general for some axion-like particle, with dark QCD phase transition, if it happens later, and also is in the pre-inflation case, and then maybe this time-dependent isocurvature perturbation could leave imprint, have some observational consequences. But that also requires some model building. Okay. So So let's just look at like actually the like I said, so what I show you is the general formula, but let's look at like this ending value for this isocurvature perturbation. That's by any value I just mean like when we look at the value when the axion starts to oscillate around the quadratic part of the potential. So then in this then the isocurvature like if expression I showed you before could be simplified to this. Okay, so that it includes two factors. One is the derivative of a log of the Rayleigh abundance of axion dark matter today with respect to the initial misalignment angle. And then the other part is just delta theta initial. It's just the primordial axion isocurvature generated during inflation, which is the ratio of the inflation Hubble and axion decay constant. So for for the vanilla scenario, when the misalignment angle is not large, say 1 or just order 1, this d log omega theta d theta is just will give us a factor of 2 over theta, okay, which I already showed you. So this is actually the one like that's commonly used, but this factor like this could give us much larger factor if the misalignment, this oscillation starts from a much larger misalignment angle. So that's a large misalignment. So if the axion rolls down the potential from near the hilltop of its potential, actually the Rayleigh abundance is more sensitive to the initial misalignment angle. Actually, this d log omega d theta part could be significantly enhanced. Actually, this could lead to much more stringent axion isocurvature constraint. Just be more precise, like I mentioned before, like when the for the initial misalignment angle odd 1, then for QC axion dark matter as a dominant component dark matter, then the Hubble is bounded to be below 10 to 7 GeV. But if you start with near the top of the potential, actually the bound is actually because its isocurvature is enhanced by this additional factor, then this Hubble is bounded to be below 100 GeV. Lastly, just want to quickly also mention that this, so far I'm just talking about the spectrum, the 2-point functions, either curvature spectrum or isocurvature spectrum. But also this, you could also just from the general solution I showed you before, you could also calculate from.
Sorry, can you stop for a second? Because this was just the only part which I barely understand. So you are saying there is an unavoidable isocurvature
in the pre-inflation case, when the axion is already present during inflation.
No, but this is unavoidable, right? Or you are saying.
So okay, again, it said that it's unavoidable in the sense that in the pre-inflation case, you have the axion already present during inflation. It will fluctuate. So its fluctuation is independent on the infinite
depends on your model of high energy physics. You are saying
so
maybe
of course you can see the post-inflation case where the PQ symmetry breaking happens after inflation. The axion is not present during inflation. So then there's just no isocurvatures to start with. So in that case, all the perturbations, okay, at least in the minimum case, all the perturbations just come from, say, in the minimum inflation scenario,
okay,
so all just come from infinite
during
perturbations.
inflation, then you have to constrain the energy scale of inflation in order not to see isocurvature today.
Yes, so in the pre-inflation case, you have the size of because the size of perturbation is depends on the inflation Hubble scale. So that's actually you could think of that as a constraint. If you want QC axion dark matter to be the dominant component dark matter, and also so that's actually in the pre-inflation case. There's a constraint on the inflation Hubble scale. So it just means depending on what the initial misalignment angle, that actually there could be the constraint could be from strong to even stronger. Okay. So lastly, just want to quickly mention that the axion perturbations, so far I talked about spectrum, but also they could it's a workout from this general solution workout the higher point functions. So the axion perturbations involve nonlinearly due to nonlinear potential. So this could produce non-Gaussian statistics for the axion isocurvature. This is different from the inflationary non-Gaussianity. Okay. which is actually small, even like in the single inflation case, single field inflation case. Okay, and I should just mention that all this formula I showed you, like for isocurvature, have been derived before, like by using much more complicated formalism, like delta n formalism, and also and all the kinds of assumptions of axion potential and background evolution. So it's this. So I think our treatment, okay, just write down this general solution, like from the field, and convert it to all this curvature, isocurvature, like actually kind of explains all this universal behavior of axion perturbations at large scales, independent of all this like model details. Okay, so that's all I want to say about this general, this analytical treatment for the axion perturbations at large scales. Any further questions? If not, I want to move on, use the remaining time to quickly mention some ongoing work. As I already mentioned, that Planck sets a strong constraint on the flat axion isocurvature spectrum, assuming QCD axion is 100% dark matter. Let's say if the initial misalignment angle is 1, the Hubble is bounded below 10⁻⁷ GeV. But of course, the isocurvature spectrum could be could be more complicated. In particular, if you consider models where you have interplay between inflation dynamics and the PQ dynamics. I won't go into all the model building details, but just to show some what kind of spectrum you could potentially get for different types of models. So you could have blue tilted spectrum, okay? Where the axion, the isocurvature, the spectrum is still parameterized as the k to some powers, but the spectral index for the isocurvature is larger than 1. Okay. Again, this is due to the PQ field could have non-trivial evolution during inflation. And more recently, we actually just for fun, we actually construct models with when axion, when the PQ field couples to the inflaton field during inflation, you could also having and the inflaton some inflaton dynamics could also lead to some funny dynamics in the PQ dynamics that could also lead to some oscillating spectrum where you don't even have this power law parameterization. Actually it's more like power law times this oscillating components. You could have sine k and sine non k. So this is work done with Xingang, Chen at Harvard, and also Lin Feng. Former postdoc Brown. So of course they could say these are just model building exercise. The real point that since we already have the data there, let's see what the data was could tell us more about the isocurvature spectrum. Okay. In particular, there's also some more recent CMB data that actually could tell us more information, shed more lights on the particle or cosmology model building. So last year there are actually 2 CMB data sets. That's ACT and SPT. This shows different spectrum TE or TE as a function of these multiples. So the Planck is shown by this green circles, and then the SPT is blue dots, and ACT is the little square, the yellow square. So both SPT and ACT do not observe the full sky, so they start from they are not sensitive to low L below 100, 200. Okay, but you could see their data extends all the way to much higher L beyond the Planck. The Planck stops around Planck stops around 2000-ish. Okay, but SPT and ACT extends all the way up to much higher L's, and with good precision even for these high L's, depending on what kind of spectrum you look at. So this data set. So one question what kind of new physics scenarios we can these new data sets could probe. Okay. So one possibility, as I mentioned, is that like the Coprobe is blue tilted spectrum. So I mentioned the blue tilted spectrum actually have more power at high K because the spectral index is larger than 1. So actually that's you actually have more power at high K or large L compared to low K if your spectrum is blue tilted. So this seems like a lecture candidate for like both ACT and SPT to probe, okay? And indeed, actually, ACT collaboration did a little bit analysis for the axion isocurvature, but we actually SPT hasn't done anything. So actually, with my collaborators, we are working actually on understanding the constraints on the blue tilted spectrum from ACT and SPT. Okay, so I want so since not some of the ranks are still like on the clusters haven't fully converged, so I'll just show you some preliminary results. So this is ongoing work with Perniti Singh, PhD student at Brown, Catherine Portretti, PhD student at Harvard, Matteo Braglia, who actually used to be a postdoc at CCA and now postdoc at CERN, and Lin Feng, visiting scientist at ICTPAP, and Xingang Chen, faculty at Harvard. So so our SPT results haven't been fully converged, but it's very similar to the ACT results. So I just show you the ACT results as an example. So what I show you here, there's a 2D posteriors after this nested sampling runnings. So the vertical axis rotation change a little bit. So I'll just so the vertical axis is actually the beta is the ratio of the isocurvature amplitude and the curvature amplitude. And the horizontal axis is the isocurvature spectral index. Okay. So what I show here is like 1 sigma and 2 sigma posterior from Planck, which is blue, okay, and ACT, which is green, and then the combined P-ACT, which is red, okay. So you can see like ACT and Planck are quite different, okay. Actually, pure ACT alone, okay, is actually because it measures the high L very precisely, and it doesn't have any low L data. It actually prefers a flat, okay, like with N equals 1, or even a redder spectrum, okay. It's still consistent with just no isocurvature at all, like with beta being 0, okay.
Is it really so? These isocurvature constraints are so weak. Like we can have like 20% of isocurvature.
No, it's not. It's not depending on the spectrum, primordial spectrum. If it's a primordial spectrum, it's flat, it's curvature.
Or if you go all the way to 0, it is pretty much 0.
Yeah. So I'm just saying the bond. Okay, this bond. Okay, is for the flat spectrum is 0.4. 0.04. The bond for this is just for any flat isocurvature spectrum.
No, but I'm just sorry. I'm asking a simple observational question.
Yeah.
What are the current constraints on isocurvature perturbations?
Yeah.
I thought isocurvature can be only very, very small.
Yes, isocurvature could is just a bond with a bond shed. Isocurvature I'm just saying the bond could be relaxed. Like if your primordial spectrum.
If you go to crazy blue tilted spectrum.
Yeah.
Okay. But if I assume.
It's just a flat spectrum. Yes, sure. Like its constraints very strong. Yeah. Right.
But is it? I'm just trying to read your graph.
So okay. So
if
you
go
look
to
at
0,
Planck. Okay. If you just look at blue, the Planck. Okay. If you just isocurvature spectral index is 1, just flat. You say it's just this. It's only allowed this is the upper bound allowed only around 0.04-ish. So say for the isocurvature spectral index 1, that's a flat spectrum, okay. So that is consistent with 0, but it says the upper bound, which is just a 95% level upper bound is around 0.04.
And CMB is the best way to measure isocurvature.
Yeah, it's currently yes.
So nobody knows that it is less than 1%. You would say. This would be not something which is known.
If it's less than 1%, sure, that's not constraint, sure.
Okay.
Yeah.
Okay, thank you.
Yeah. Okay. So actually Planck Planck actually prefers compared to ACT actually prefers the bluer spectrum. Okay, it still allows spectral index probably not 4, but at the 2 sigma level, like a spectral index like 3, pretty blue tilted. And when you combine these two, okay, Act and Planck, actually that's showing these red regions. Actually, so you see that the parameter space for blue tilted spectrum it shrinks, okay, like compare the red to the blue one, but not that much. So it's actually the combined result is actually still closer to Planck than to Act.
Well,
Okay.
on this spectral index, white noise is 3 or is 3/2?
So sorry, was 3?
If I think of like a white noise power spectrum
Oh,
versus
yes,
curvature, in this parameterization, would it be?
This parameterization, it's 3.
It's 3 here.
Yeah, 3 here. Yes. Yes. Okay, that's a good point. Yes. So the reason, okay, I just want to say lastly, I want to say the reason why this combined result is still closer to Planck than like the Act, okay, is really just due to the isocurvature transfer function, okay. So actually the isocurvature transfer function. To go from the primordial spectrum to the CMB spectrum, you need to convolve the primordial spectrum with the transfer function. So the isocurvature transfer function actually decays faster than the adiabatic one. Here is this 2-bit plot. I won't go explain in detail. This shows the transfer function as a function of k for different L's. Then the solid curve, the different colors corresponds to different L's, and the solid curve for each color is the curvature transfer function. The dashed line is the isocurvature one. Okay, it's not very clear, I guess. Maybe just look at the orange one corresponding L equals 21. So the solid like spiky ones are the curvature transfer function, and then the adiabatic transfer function. The dashed line is the isocurvature transfer function. So you could see the isocurvature dashed one actually decays faster than the solid ones. So that means even for blue tilted spectrum, because the transfer functions actually like decays faster, you still have some you still have constraining power from relative low L's like the Planck data sets. So that's why the combined result, the Planck plus Act, is still closer to Planck than to Act. That's actually all I want to say. So I'll conclude. I just show you a simple analytical explanation for the universal behavior axion perturbations at both curvature and isocurvature at large cosmic scales that actually hold for all broadcasts and models with different axion potentials and different cosmic background evolutions. And also just quickly show you that's actually more arena to explore for axion dark matter isocurvature beyond flex spectrum in both terms of model building and the data analysis. That's all I want to say. Thank you for attention.
So we have time for a couple more questions for Jiji.
So, what about non-Gaussianity? You said that the curvature can be very non-Gaussian.
Yes.
So is it possible the scenario when with some crazy spectrum that one first sees this non-Gaussianity and only later realizes that actually that was the curvature? Is it possible?
I think okay. So first, you still need to to avoid. So you have to do something to the spectrum, right?
Yeah,
to avoid.
some
So that's all I'm
yeah.
saying. Like blue tilted, all
Right,
this
yeah,
oscillating
right.
behavior. And sure, like actually, I don't know whether we haven't really done the full data analysis. So but somehow we're thinking about whether you could have these scenarios where there's somehow either due to blue tilted or due to some oscillations that actually the 2-point function is not the first thing you see. Actually the 3-point is the first things you see, but it's probably challenging. I would just say in terms of models, you could construct models where your spectrum is not flat, and then you still have non-Gaussianity. But just from data point of view, whether the 3-point would be the first for you to see isocurvature, I'm not. I cannot guarantee there's a scenario here.
David?
Yeah, I guess I had a question about kind of just the vanilla bound of H inflation less than 10⁻⁷ GeV case. So how do I understand that if, say, inflation or reheating is very efficient, right, then the temperature after that is the geometric mean between M Planck and that, which is above FA, and for the normalization you gave, right? Right, because it was, It was 10 to 11. It was on like
let's
10 to
see.
11 jet. So in that case, the symmetry is PQ symmetry is restored. Do I have bound still, or what?
Oh,
what
okay,
happens
okay,
there?
sure,
How is that
sure,
consistent?
okay. So you're saying, so it's also said like, I won't even call that like pre-inflation, that's just post-inflation. The PQ symmetry is restored during heating. But like for the case you mentioned, like just that's like, yes, if you assume like a super efficient reheating, but if I just think about like reheating through a dimension 5 operator, the scaling won't be like that, what you just said. So I just say, sure, if you could reheat to high temperature above the FA, sure, then you could restore PQ symmetry, and then even if you have axion as a curvature, if you have like axion during inflation and have axion as a curvature, it will be wash out if you could restore the PQ symmetry.
Okay.
Yeah, sure, that's a one possibility. Yeah.
Yes. If not, let's thank Jiji again.